All right, let's continue on with the second law today. Going to finish up, I hope we can finish up all the material regarding the second law. So for today, let's go over the Carnot heat pump and refrigerator. Yes, there's a Carnot heat pump and refrigerator. Why? Because we can take a Carnot heat engine, which takes energy from a high temperature reservoir, produces work, and rejects a certain amount of energy in the form of heat to a low temperature reservoir. We can reverse the Carnot heat engine to produce a Carnot refrigerator or heat pump. We'll talk a little bit about that in a moment. Then we're going to move on to a reformulation of the second law of thermodynamics in equation form. Remember, the second law dealt with a bunch of pictures, the Clausius and the Kelvin-Planck pictorial representation or statement of the second law. We're going to actually reduce these pictures into an equation. So that's called the Clausius inequality. We'll do a little example reinforcing that the Clausius inequality is simply an equivalent mathematical restatement of the pictorial representation of the second law. So we'll do a little example involving the Clausius inequality, show you how to use the Clausius inequality. And then I think if we have time, we'll do a short review of second law material to give you kind of an overview of what we've done for the last week. So the Carnot cycle, remember we had the Carnot heat engine. So let's put the cycle, let's put the, so we have the Carnot heat engine. So remember the Carnot heat engine takes heat from a high temperature reservoir, operates in a cycle. So this is a Carnot heat engine, takes a certain amount of heat from a high temperature reservoir, produces a certain amount of work over a cycle, and rejects the remaining energy into a low temperature reservoir. Okay, so that's the Carnot heat engine. This engine is reversible. So there's no sources of irreversibility while this device is running, no friction, no unrestrained expansion, no heat transfer across a finite temperature difference. These are all the reversible processes that we've illustrated. The TV diagram, as you recall, for the Carnot cycle, so we have TV. So we start at state 1, which is the working fluid at a temperature T high. Start at state 1 at the minimum volume, and then we expand it to state 2 isothermally. So this is where the heat transfer is being performed from the high temperature reservoir at TH. And then we have a adiabatic expansion. So we have an adiabatic expansion from state 2 to state 3 down to the low temperature reservoir temperature, TL. And then we have isothermal compression, where we reject heat to the low temperature reservoir, QL. Again, the system, the working fluid inside the Carnot heat engine, our piston cylinder device that operates frictionlessly, slowly, so there's no unrestrained expansion and there's no heat transfer across any finite temperature differences because all the heat transfers occur at either the high or the low temperature reservoir temperatures. And then we complete the cycle by having adiabatic compression back up to state 1. So that's the Carnot heat engine, Carnot cycle for a heat engine. So this is reversible because it contains no irreversibility, so let's reverse it. So this is the Carnot heat pump or refrigerator. Carnot heat pump or refrigerator. So what we're going to do instead is we're going to reverse this guy, reverse the Carnot heat engine to produce a heat pump or a refrigerator. So let's reverse all the heat and work interactions. between our high and our low temperature reservoir. So here we have a Carnot heat pump or refrigerator, Carnot heat pump or refrigerator. It receives a certain amount of work over the cycle, extracts a certain amount of heat from the low temperature reservoir, and dumps a certain amount of heat to the high temperature reservoir. If you apply the energy balance, you'll see that Q high is equal to Q low plus the cycle work. Okay? Likewise, if you apply the energy balance on the Carnot heat engine, you'll find that the heat rejected to the low temperature reservoir is the heat received from the high temperature reservoir minus the cycle work. Okay? So that's a Carnot heat pump or refrigerator. The TV diagram here. Now let me actually get a process, make sure I have the, yes. So the TV diagram here, state one starts off in the same place. So state one is still the minimum volume, maximum temperature in the cycle. But instead of going isothermal heat addition, we're going in the opposite direction. We're going counterclockwise through the cycle instead of clockwise. So we start off with an adiabatic expansion. Adiabatic expansion down to the low temperature, reservoir temperature. We now expand the working fluid isothermally, receiving QL from the low temperature reservoir. So that's expansion from state 2 to state 3. Then we have adiabatic compression. Adiabatic compression up to the high temperature, reservoir temperature, TH. And then we finish off the cycle. Finish off the cycle with isothermal compression, rejecting QH to the high temperature reservoir. Okay? Cycle diagram is qualitatively similar, except in the case of the heat engine, the cycle goes in the clockwise direction, and in the case of the heat pump or the refrigerator, the cycle goes in the counterclockwise direction. Okay? So that you can reverse the Carnot heat engine and produce a refrigerator. There's a good example, a detailed example in the notes involving detailed cycle analysis of a Carnot refrigerator or heat pump. So you should have a look at that. Needless to say, one last little thing. Needless to say, the efficiencies of the Carnot heat engine, so let's remind you how to calculate the efficiency for the Carnot heat engine. Carnot heat engine is reversible, so the efficiency of the Carnot heat engine is the efficiency for a reversible heat engine, which is 1 minus QL over QH for a reversible process, or if you like, 1 minus T low over TH, okay? So remember, the efficiency for a Carnot heat engine, very similar, very simple expression. So eta Carnot or eta reversible is 1 minus T low over TH. The coefficients of performance for a Carnot refrigerator or heat pump. So Carnot, let's do a heat pump here. Carnot heat pump, COP. So Carnot heat pump. The coefficient for performance for a Carnot heat pump, that's going to be equal to, let's see, a Carnot heat pump is tasked with lifting heat and rejecting QH to a high temperature place. So the emphasis is on the high temperature heat rejection, and then the cost is the work over the cycle. And so that ends up being what? 1 over 1 minus QL over QH when you apply the energy balance. Work cycle is QH minus QL. QH minus QL. So then I divide top and bottom by QH and I get 1 minus QL over QH. Remember, the Carnot cycle is reversible. So this is reversible, and this is reversible. Okay? And that gives me 1 over 1 minus T low over TH. So the COP for a Carnot heat pump, COP for the Carnot heat pump is equal to 1 over 1 minus TL over TH. I will leave it to you to develop the expression for the Carnot refrigerator. All that changes for the refrigerator is we have a QL up here in the numerator. So I guess you would have, this is QL and this is QH minus QL. You get a QH over QL minus 1. So that would give you a TL over TH over TL minus 1 in the denominator here instead. So there'd be a TH over a TL minus 1 in the denominator for the Carnot refrigerator. Okay? All right, let's try to get a little bit more distance here between these pictures that we have about the second law, and try to get to a little bit more solid footing in terms of mathematics. Something a little bit disconcerting about designing your devices, your heat pumps, your refrigerators, by referencing pictures which tell you what is and is not possible. We do have the ratio of the heat transfer being equal to a ratio of temperatures for a reversible process. That helps. But it would be nice to get rid of the pictures entirely and express the second law purely in mathematical form. That's what we're going to do today. So let's say we have the following situation here. I have a single reservoir at a temperature TR. Single reservoir at a temperature TR. It's a reservoir temperature TR. Now, this reservoir rejects, or you can extract, a certain amount of heat. I'm not going to write Q here. I'm going to write del Q. I'm going to make this a differential process. And if we have to convert that to an overall process, we can simply integrate. So I want to be as general as possible by doing this for a differential process. So a certain amount of heat, del QR is transferred from this reservoir. Now, this heat flows into a reversible heat engine. So this is a reversible heat engine. Okay? Now, what I'm also going to do here, I'm going to stick a thermometer right there. I'm going to stick a thermometer right there. And I'm going to measure that temperature. I'm going to measure that temperature. And I'm going to state here that that temperature is always equal to the reservoir temperature. Okay? It's the reservoir temperature. TR. So the temperature right there is equal to the reservoir temperature. Why is it equal to the reservoir temperature? Because this is a reversible heat engine. In order such that there is no temperature gap between the reservoir and the heat engine, this temperature must be TR. If this is a reversible device, then we can't have heat transfer across a finite temperature difference. That temperature right at the surface of the heat engine where del QR is received has to be the reservoir temperature. Okay? Now, this reversible heat engine takes some of this heat, del QR, and produces a certain amount of work, del W, and I'll call it reversible. Del W reversible, indicating that this is heat, this is work being produced by the reversible heat engine. Now, of course, this reversible heat engine as it stands violates the Kelvin-Planck statement of the second law. We only have heat being transferred from a single reservoir. We don't have any heat being rejected. So I'm going to reject some heat. Okay, I'm going to reject some heat here, and I'm going to call this heat del Q. So I'm going to call that heat del Q. I'm going to call that heat del Q. Now, below this heat engine, the reversible heat engine, I'm going to place an irreversible or reversible. I'm going to put a general heat engine down here, which may be reversible or irreversible. Reversible or irreversible. I know you can't see that, but just write it down in your notes. So this is a heat engine, which may or may not be reversible. It could be irreversible. Of course, this guy is receiving a certain amount of heat. I'm going to stick a thermometer right here. I'm going to stick a thermometer right there and call that temperature T. Okay? Now, this irreversible or reversible heat engine also produces a certain amount of work. I'm going to call it del W. So we got two works being produced, differential amounts of work, del W reversible and del W, one from a reversible heat engine and one from a possibly irreversible heat engine. Okay? Now, I'm going to surround this. That's it. Notice there's no second reservoir here. All right? So I'm going to surround this thing with the control volume. We've done this kind of thing before. And this represents an equivalent device. Let's write the equivalent device here. Here's our reservoir with temperature TR. We are rejecting a certain amount of heat, del QR. And then we have this device, which is producing a net amount of work, del W reversible and del W. So del W net is del W plus del W reversible. Okay? Also, from the energy balance, you can clearly see from the energy balance here, E balance on our composite system. On our composite system, the E balance says del Q reversible minus del W net is equal to dE. That's what the energy balance says regarding our composite system made out of a reversible and a possibly irreversible heat engine. Now, let me point out one or two more things here. So we got the energy balance. Check. Got the energy balance. Differential form. Since the reversible heat engine here interacts with a reservoir and another heat engine, we have two temperatures here. We got the reservoir temperature and we have the temperature T. Because it's reversible, so because this guy is operating reversibly, we get that the ratio of the heat transfers, del Q over del QR over del Q. So note, reversible heat engine. The first one's reversible. This means del QR over del Q, and this is for a reversible process, is equal to TR over T. Okay, reversible process going on here as far as the reversible heat engine is concerned. So that ratio of heat transfers, del QR over del Q has got to equal TR over T. Now I'm going to solve that here. I'm going to solve this for del QR. The differential heat transfer from the reservoir is equal to del Q TR over T. I'm just solving this for del QR. I'm just solving this for del QR. All right, so this is the energy balance. It's equation number 1. This is the reversible heat transfer result. That's equation number 2. What I'm going to do is I'm going to integrate the energy balance over a cycle. I'm going to run that thing over a full cycle so that we don't have differential heat transfers, but overall heat transfers. So I'm going to integrate the energy balance over a cycle. Let's see what we get. Let's integrate the energy balance over a cycle. So over a cycle, integral. See this loop here on the integral? That means a cyclic integral over a cycle. Cyclic integral, del Q reservoir, or del QR, minus cyclic integral, del W net, is equal to the cyclic integral dE. So again, this loop on the integral means a cycle. What's the total change in energy, which is a path, which is a point function? What's the total change in energy over a cycle? What's the change in any point function over a cycle? 0. So this is a cycle. It's a cyclic process, so that's 0. Well, I'm going to stay right here. I'm going to leave this integral here for del QR just for a moment. The integral of the work, this is the net work over the cycle. So W net, and that's over a cycle. Okay, W net over a cycle. The first integral, the heat transfer integral, I'm going to substitute equation 2 into the integral of del QR. Remember, equation 2 gave us the differential heat transfer del QR is equal to del Q TR over T. So I'm going to substitute that into my heat transfer, integrated heat transfer for my composite device. So I have a cyclic integral, and I have TR over T, and I have del Q. Okay, that's what my cyclic integral for the heat transfer becomes. All right, let's write what we have left over. I'm going to take the work term, W net, for the cycle, and I'm going to stick that on the right-hand side of my equation. So I'm going to get the integral of T reservoir over T del Q equals the net work over the cycle. Now, what value can W net over the cycle be? Let's go back and have a look at our composite device. So here's our composite device. It receives heat from a reservoir, a single reservoir, and produces work. Over a cycle, this guy cannot produce positive work. That would be a violation of the Kelvin-Planck statement of the second law. This guy, over a cycle, receiving heat from a single reservoir and producing the equivalent amount of work is not possible according to a Kelvin-Planck statement of the second law. So from Kelvin-Planck, W net over the cycle cannot be positive. It cannot produce work. So W net cycle can either be 0 or it can be negative. And this is according to the KP, Kelvin-Planck second law. Kelvin-Planck statement of the second law. That work has to be negative or 0. The device can either do nothing or it can receive work. You can do work on it and it produces the equivalent amount of heat. So that means, forgot over a cycle, be careful here. So that means the integral of T reservoir over T del Q has got to be less than or equal to 0. Now, one last little step here before we finish up. The reservoir temperatures for the reservoirs are in absolute terms. They're in Kelvin or Rankine. There's no such thing as a negative absolute temperature. That means I can extract out the reservoir temperature from the integral. The reservoir temperature is constant, so I can extract it out of the integral. And then I can divide both sides by the reservoir temperature to get rid of TR. So I'm going to extract this out. So we have TR integral del Q over T over a cycle has got to be less than or equal to 0. And then I'm going to divide both sides by TR, and I still get an integral which is less than or equal to 0. So let me write this over here. So let's divide by TR. So the integral of del Q over T over a cycle has got to be less than or equal to 0. Let's write that equation again right over here, and we'll write it big. That equation is called the Clausius inequality. Clausius inequality. Clausius inequality. The integral of the heat transfer into a system divided by the temperature of the system, or the temperature at which the heat was transferred, has got to be less than or equal to 0. This is your Clausius inequality. Put a box around it. That's an important result. Why is this important? We've gotten rid of the pictures. I don't need the Kelvin-Planck statement anymore. I don't need the Clausius statement of the second law. I've got this inequality involving an integral. I've got a mathematical statement, an equation, which is based on and equivalent to the second law of thermodynamics, either the Kelvin-Planck or the Clausius version. We're going to prove that in just a moment, or I'll demonstrate it to you in just a moment. Now, for those of you that are still a little woozy on this, maybe you're not very satisfied with this Clausius inequality instinctively, I don't blame you. It's weird. It's not an equality, it's got an inequality in here. This is not the best engineering equation to use because it's got an inequality in it. It's just weird. What do we do with this inequality? Don't worry. In the next lecture, we will get rid of this inequality and we'll be instead looking at a conservation equation with an equality in it, an equal sign, involving a new property called entropy. So this Clausius inequality paves the way for the existence and a hypothesis and existence of a new property called entropy. So don't Don't despair with the inequality there. We're going to get rid of that in the next lecture. Let's show that this quasi-inequality is consistent and implies the second law in pictorial form. Let's use this Clausius inequality here on a simple case. Let's say I have a high temperature reservoir and a low temperature reservoir here. Now, let's say I have a device. This is a magical device. It's called a Clausius violator. Clausius violator. It doesn't exist. It's a magic device. What does this device do? Not really. It takes a certain amount of heat, QL, from a low temperature reservoir, and magically, without work, shoves it up to a high temperature reservoir. It's not possible. That's why it's called a Clausius violator. So make sure you understand here, this thing is impossible. Not possible. I'm going to put that in parentheses just so we're clear about that. Okay, that thing is not possible. It's Clausius violator. Violates the second law of thermodynamics, Clausius version or Clausius statement. Let's apply the Clausius. Let's try to calculate this integral. The cyclic integral del Q over T to this device. So here's my device right here. If I put a thermostat here, thermometer, and I measure the temperature here, I'm going to get T high. And if I measure the temperature here, I'm going to get T low. So I'm going to put two thermometers here and measure the temperature. And I find the temperature at the top of the Clausius violator where it rejects QH, that's TH, and the temperature at the bottom where QL is accepted from the low temperature reservoir. I measure the temperature right there, and that's TL, okay? So let us evaluate this integral for this device, the Clausius inequality, Clausius violator. So the cyclic integral evaluated, integrating the differential heat transfer over the interaction temperature. Let's evaluate this for this device. Now this device receives heat from one place, the low temperature reservoir. And the temperature at which the heat is at when it is received is TL. This guy here is what's called the interaction temperature. The temperature right here at the location where the heat flows into the Clausius violator. I put a thermometer right here and the temperature is TL. So the heat transfer from the low temperature reservoir, I'm going to break this integral up into two pieces. Del Q over T. The first piece is going to be evaluated for the heat transfer from the low temperature reservoir. So I'm going to write low temp heat transfer. And then heat is being rejected at a temperature TH. TH is the interaction temperature, the temperature at which the heat is rejected from my Clausius violator. So I'm going to have a negative. Why negative? Because heat is being rejected. Integral del Q over T, and this is going to be for high temp. High temp heat transfer. So I've broken up my cyclic integral and I've looked at each heat transfer separately in the cycle. Now the interaction temperature at my high temperature heat transfer point is a constant and it's equal to TH. I'm sorry, T low, low temp. The interaction temperature is a constant. The temperature here isn't changing. It's always TL. This thing is running in a cycle. Temperature is always the same. So that temperature down there is TL. At the high temperature or high heat transfer, QH, the temperature, the interaction temperature is TH. Okay, and that's constant. So if these temperatures are constant, I can pull them out of the integral. Minus 1, plus, sorry about that, equals 1 over TL integral del Q, and this is the high temperature heat transfer, minus 1 over T8, low temp. Okay, yeah, I want to make sure I've got this correct. Low temp is where heat is being received, so this is the low temp heat transfer. This is the high temp heat transfer out of my system. Okay. Interaction temperatures are constant, so I pull them out of the integral. The total heat transfer, the integral of the differential heat transfer into my system from the low temperature reservoir is QL. That's the total heat transfer over the heat addition process. The total heat transfer over the heat rejection process is QH. So I have QL over TL minus QH over TH. Now, if you apply an energy balance to this Clausius violator, there's no work going on, so QH has got to be equal to QL. So this guy here is equal to QL. So let me factor out QL and write what I have left over. 1 over TL minus 1 over TH. Now, QL is positive, it's a positive heat transfer. I've dealt with the signs of the heat transfers with this negative sign. There's a negative sign in front of this Q high out of the system right there. So the negative sign, the signs on the heat flow are taken care of with this negative sign here. QL is positive. Now, this term here, 1 over TL. TL is a lower temperature than TH. That means that 1 over TL is a greater numerical quantity than 1 over TH. This guy is bigger than this guy. So this whole thing is greater than 0. In other words, for this Clausius violator that violates the Clausius statement of the second law of thermodynamics, I apply the Clausius integral. I integrate Q del Q over T, and I find that del Q over T is greater than 0 for this Clausius violator. Does this result, del Q over T for this device, satisfy the Clausius inequality? Nope. The Clausius inequality says that this integral has to be less than or equal to 0 for any device. Violates Clausius inequality. Violates Clausius inequality. This device is not possible, according to the Clausius inequality. So the Clausius inequality is a mathematical reformulation of the pictures or pictorial statement of the second law of thermodynamics. We don't need the pictures anymore. We got the Clausius inequality, and it says the same thing. You could do a similar proof for the Kelvin-Planck statement, a Kelvin-Planck violator. You could do a similar thing for the Kelvin-Planck violator. That's pretty easy to do. There's only one heat interaction. You'll get Q over T. Q is positive, T is positive, so you'll get a single heat transfer term, and this cyclic integral will be positive. So you could do this with a Kelvin-Planck violator, and you'll also get that this cyclic integral is positive, which is a violation of the Clausius inequality. So the Clausius inequality, let me write it one more time, just so we're on the same page. Let's write the Clausius inequality one more time. Is equivalent to all those pictures that we saw. The Clausius, Kelvin-Planck statement of the second law of thermodynamics. So Clausius inequality. Integral over a cycle of the heat transfer divided by the temperature T has got to be less than or equal to 0. That's our Clausius inequality. It is equivalent to the second law of thermodynamics. All right, speaking of which, let's just take a moment to review all that we've done in this chapter. This has been kind of a strange chapter, I'm sure you'll agree. It started off with a bunch of pictures, a bunch of talk about reversible and irreversible processes. Kind of a strange chapter. I hope you made it through, because now we're going to apply what we've learned, and hopefully what we're getting more comfortable with, to derive the existence of a brand new property, and then we're going to be using it throughout the rest of the semester. That property, as you may have guessed, and I may have said many times, is entropy. So let's do a little review here. So second law, material review. Let's just go through and review some second law stuff. So we started off talking about reversible versus irreversible processes. Irreversible processes are processes that in nature proceed in one direction only. All processes that involve friction, unrestrained expansion, or heat transfer across a finite temperature difference are not reversible. They are irreversible. They occur in nature for isolated systems in one direction only and not the other. So we started off by defining three irreversible processes. Irreversible, processes. Irreversible processes. What was the first one? It was processes involving friction. Another one was unrestrained expansion of a gas, or just unrestrained expansion. It's also fast compression, by the way. Either a quick expansion or a quick compression is irreversible. Quick expansion, I think, is probably the easiest one to understand. And then we have heat transfer across a finite temperature difference. So HT across a finite, what I mean by finite is measurable, finite, quantifiable, finite delta T temperature difference, all right? These are all processes that are irreversible. So after we've introduced this, we then moved into pictures or images about what kinds of processes cannot occur in nature. Those things, irreversible processes, occur in nature. So what does not occur in nature? So that's where the second law comes in. So second law. And there are two versions. There's the Kelvin-Planck statement, which says you have a reservoir at a temperature, let's say TR. It rejects a certain amount of heat into a cyclic device and produces a net amount of work. The second law says that this is not possible. This is the Kelvin-Planck statement of the second law. So KP statement of the second law, Kelvin-Planck. The other statement of the second law refers to heat transfer from hot to cold. The Clausius statement says that you cannot have heat move from a low temperature reservoir to a high temperature reservoir without the application of work over a cycle. So we have QH, we have QL, they're both the same. You cannot build a device, a workless device that operates over a cycle, which transfers heat from a cold place to a hot place. So this is not possible. This is the Clausius statement. Clausius statement. Kelvin-Planck statement of the second law, Clausius statement of the second law. Okay, not possible. Then we shifted gears to ask ourselves an auxiliary question. What is possible? And what we want to know is mathematically what's possible. This is not possible. What is possible? What is on the limit of possibility? What is on the limit of possibility? Well, what we showed was for any work-producing device. So what is possible? Well, what I mean by that is the maximum efficiency for some heat engine. I'll put HE here. The maximum efficiency, HE max. I guess I'll put max. And what I mean by that is the efficiency of a heat engine. The maximum efficiency is equal to the efficiency of a reversible heat engine. And that efficiency is equal to 1 minus QL over QH for a reversible process. And this ratio, QL over QH reversible, is TL over TH. So this is 1 minus TL over TH. There are equivalent expressions for heat pumps and refrigerators. So COP max for a heat pump or refrigerator. There are equivalent expressions for maximum efficiency of a heat pump or refrigerator. Those efficiencies are equal to that of the reversible refrigerator or heat pump. You can go back and look at your notes on the expressions involving TL and T high for a reversible heat pump or refrigerator. The next question after that is, if we were to not build, but visualize or analyze a conceptualized heat pump, refrigerator, or heat engine, how might it work? Forget building a reversible heat pump, refrigerator, or heat engine. How might we envision a reversible device that produces the maximum work, has the maximum efficiency, or the maximum coefficient of performance? That led us to the Carnot cycle. Carnot cycle. I'm not saying you can build it. You can't build this thing. You can approach it. You can build something close to it. But the Carnot cycle is a reversible heat engine, heat pump, or refrigerator. It can't really function in nature, but we can approach it. So how does it work? What might we conceive of a reversible heat pump or refrigerator? Well, this heat pump or refrigerator, let's say it's a heat engine. So we have QH, QL. It produces a work net. And this is a Carnot heat engine. Carnot heat engine. The efficiency for this Carnot heat engine is equal to the efficiency of the reversible heat engine. So that's 1 minus TL over TH. Okay? What are the processes involved with this Carnot heat engine? We start with isothermal heat addition from the high temperature reservoir. System starts off at the high temperature, isothermal heat addition from state 1 to state 2. Then we have adiabatic expansion from state 2 to state 3. And the expansion is all the way down to temperature TL, the low temperature reservoir temperature. And then we have compression, isothermal, so that's where we reject the heat, the low temperature reservoir. And then we have adiabatic expansion back up to the original temperature and volume. Okay, so that's the TV diagram for the Carnot heat engine. And this is operating in the clockwise direction. Okay. Needless to say, the Carnot heat engine cannot contain any irreversibilities, no friction, no unrestrained expansion of the working fluid. That means the piston, this guy actually is a piston cylinder device. So let me actually draw. So this Carnot heat engine uses a piston cylinder device, some sort of gas in here, let's say. So there is a piston cylinder device inside the Carnot heat engine. If there's no unrestrained expansions, that means the piston has to move very slowly. You can't be yanking on the piston or pushing it down very quickly, else you get unrestrained expansion or compression. So it has to be very slow in operation. So the Carnot heat engine contains no processes involving friction. No friction. No unrestrained expansion. What does that mean physically? That means it has to operate very slowly. Slow operation. Slow operation. How slow? So slow you can't see the piston moving, in theory. Very slow operation. By the way, that means this thing, it's efficient, but it may not be powerful. If it turns so slowly you can't even see the piston moving, it's not going to produce much power. How do we get rid of the friction? Well, well-machined parts, good lubricants, you can minimize friction. Perfect machining. Perfect machining. Perfect lubricant. Perfect lubricant, okay? And then, of course, the third source of irreversibility is heat transfer across a finite temperature difference, a measurable temperature difference, and that is not present as well. No heat transfer across a delta T, a temperature jump. That's why we have heat transfer at TL or TH. Okay, heat transfer at TL or TH. Heat's not going to flow very fast at all. It's slow. It doesn't produce much power. Okay, so this is the Carnot cycle. There's also the Carnot, this is the Carnot heat engine. There's also the Carnot refrigerator and heat pump, which work in the counterclockwise direction. Just reverse the signs on all the arrows here, and it becomes a heat pump or refrigerator. It's reversible. It's a Carnot heat engine. It's reversible, so there's no reason you can't do that. So after talking about developing a device, not building, but maybe conceptualizing such a device, we then decided to finish off by trying to get away from all these pictures, all these control volumes and reservoirs into a single compact mathematical statement of the second law of thermodynamics. So that brings us to the Clausius inequality. Clausius inequality. Clausius inequality. The integral over a cycle of del Q over a temperature T has got to be less than or equal to 0. Again, I'm going to box this up. Very important result from the end of our treatment of the second law. Okay, I hope we've tied this up a little bit. This has been kind of a strange chapter. Maybe you're anxious to be over with it. We're going to move on to chapter 6 of the notes, which is entropy and the entropy balance. And that's going to open up a whole new world of analysis. We can start doing real thermodynamics. Tough stuff. Going to make the energy balance look simple. Tough stuff, but good stuff. Good stuff. So we're going to leave it here. We'll pick up and begin chapter 6 in the next lecture. Take care, ladies and gentlemen.